Good afternoon, everyone. Am I clear to all of you, please?
Yeah, I can hear you.
Yeah, thank you so much. Uh, Maybe most of our fellows will join on the way. However, I would like to introduce myself. I'm Dr. Nazir Muhammad, currently serving as an assistant professor in the Department of IT and Computer Science at PAK Austria Fachhochschule Institute of Applied Sciences and Technology in Haripur. I'm honored to be the moderator for today's webinar, representing the ECO Science Foundation and the Union of Iranian Societies of Mathematical Sciences. This marks our sixth lecture in the series on popularizing mathematics and science. As a member of the executive committee of the joint partnership between ECOSF and UISMS, I welcome you all. For those joining us for the first time, let me briefly introduce the ECO Science Foundation. It is a specialized agency of the Economic Cooperation Organization, an intergovernmental entity with 10 member states, including Afghanistan, Azerbaijan, Iran, Kazakhstan, Kyrgyzstan, Pakistan, Tajikistan, Turkey, Turkmenistan, and Uzbekistan, mandated to promote science, technology, and innovation amongst the ECO member countries. Before we begin, a quick request, kindly keep your microphone muted throughout the session. If you have any questions, feel free to share them in the chat box and we will address them during the question and answer session at the end. Today, we are privileged to have Dr. Imran Anwar, Chair and Associate Professor in the Department of Mathematics at Lahore University of Management Sciences, LUMS, Lahore, Pakistan, as our esteemed speaker. Allow me to provide a brief introduction to Dr. Imran Anwar. He earned his PhD in commutative algebra from the prestigious Abdul Salam School of Mathematical Sciences in 2008. His academic journey includes serving as an assistant professor at the ComScience Institute of Information Technology Lahore campus until 2015, followed by his role as an associate professor of mathematics at the Abdul Salam School of Mathematical Sciences from 2015 to 2020. In 2021, he assumed the position of associate professor and chair of the Department of Mathematics at the Syed Babar Ali School of Science and Engineering, LUMS, Lahore. Under his leadership, the department achieved noteworthy recognition, being acknowledged as the emerging regional center of excellence by the Commission for the Developing Countries of the European Mathematical Society. Dr. Anwar also played a key role in the department designation as an ICTP affiliated center by the Abdul Salam's International School for Theoretical Physics in Trieste, Italy. His commitment to fostering a global perspective in mathematical research is evident through his role as an ambassador for the International Day of Mathematics in Pakistan. Let me speak out a little more about him. In addition to his academic endeavors, Dr. Anwar has curated the LUMS Math Circle, an initiative aimed at cultivating mathematical interest among school students. Through these efforts, he remained dedicated to advancing mathematical education, research, and collaboration on both regional and global scale. I would like to request Dr. Imran Anwar. Please, sir.
Thank you very much, Dr. Nazir, for a very kind and generous introduction. And I'm humbled to be here. And I would like to thank the organizer for providing this opportunity to present a talk on math popularization, which is very close to my heart. And in this prestigious gathering, I welcome all the participants who spare their time, and I try to make this talk as valuable as and comprehensible for the audience as possible. So I start. So as the title of the talk suggests that so this talk will uh, will provide you a brief journey of mathematics, our different eras, and definitely the most important thing why mathematics is so important. It deals with the thought process. So let's start with a very light story, and the story is from the famous speech of David Foster Wallace about the three fish. So two young fish, you can see in the picture, they came across an older fish, and the older fish nod at them and say, "Hey, hello boys, good morning boys. How's the water today?" And the two young fish swim along in their own direction, and one of them look at the other and ask, "What the hell is water?" So the main thing is that the hardest question or hardest point in general day life or even in sciences is to understand the most trivial thing we are living in. So the two young fish are not familiar with the importance of the water until unless they came across the question, how is the water? So thinking has been a very, very important role in the development of mathematics and philosophy all during the different eras. So I would like to start with this particular point where mathematics and empirical thinking was taken the place from the work of Aristotle. Aristotle was always thinking about what is the logic, how to deal with the thinking process, and he wrote six books, and they are known as Organon, where he used logic to to hone the thought process. And later on, René Descartes, he introduced the Mathesis universalis. That is a hypothetical universe which is modeled on mathematics, and it was envisaged by Descartes and later on by Leibniz. And what René Descartes has given after Aristotle, he has given the rules of the direction of mind. So you can search, you can find the rules by René Descartes how to think, rules and direction of the mind. And later on, a very phenomenal figure is George Boole. He gave the laws of thought, and again, what he has done, George Boole fully accepted and endorsed Aristotle logic, and he gave it to the mathematical formulation, and that gave the theoretical mathematical theoretical background for the logic and probabilities which is being taught at the university level. And the major philosophy what Boole got is to go under our and beyond. This is the main slogan of studying the mathematical study of any particular topic. So Boole's work founded the discipline of algebraic logic, and George Bullock's work shown us and to the mathematics as a most creative and forward-looking subject. And with the work of George Boole, people started viewing mathematics, and now that's why mathematics is reflected in almost all branches of sciences, particularly when it comes to this decision making. Whenever there is a thought process involved, so there is a mathematical structure which is usually developed on the light which was shown by George Boole. Okay, this is some serious way of thinking which started. So one can read about organons, one can read about rules and direction of the mind by Rene Descartes, one can read about Law of Thought, the book by George Boole. And let's talk about the interesting quotation. So because we are talking about George Boole, so George Boole said that, and there is a fun element too. So, interesting quote. First of all, let's go to the serious part. The general laws of nature are not, for the most part, immediate for perception. So, you can't deduce anything or laws from perception. And according to Richard Feynman, to those who do not know mathematics, it is difficult to get across a real feeling as to the beauty, the deepest beauty of the nature. If you want to learn about nature, to appreciate nature, it is necessary to understand the language that she speaks in. Okay, these are the two important quotation which is highlighting mathematical role, and but their wife are not so happy with them. So first we talk about the wife of Richard Feynman, and Richard Feynman's wife just complained a divorce against him, and that was a complaint which was written in the divorce complaint. He begins working calculus problems in his head as soon as he awakens. He did calculus while driving in his car, while sitting in the living room, and while laying in the bed at night. So that's why Feynman's wife was not happy with him and wanted a divorce. And what happened to poor George Boole? In the late 1864, Boole walked in heavy rain from his house to the university, which is 3 miles away from his home place. And because he was getting late from the lecture, so he lectured wearing his wet clothes, and he soon became ill and developed pneumonia. Now, he was a very good logician, but he could not teach logic to his wife. His wife believed in the remedies should resemble their cause. So, this is a very, very old philosophy where people used to uh, it- cure the diseases by looking at the causes, and that there was a hardcore belief was there that any disease which come from a cause, that cause will cure it. So his wife was a strong believer of that, and the poor guy was wrapped up in wet blanket because the wetness brought him the disease. So his wife thought that the remedy should be following the same pattern from where he got the sickness. So she wrapped him in the wet blanket, and the wet having brought on his illness, so Bully's condition got worsened and he died at 8 December. Okay. So this is the important part. This is their wives were not happy with mathematicians when they, and one is not happy, the other poor guy got who brought the logic in math, the Aristotle, but he could not teach the logic to his wife, and his wife logic killed him. Anyways, let's move to the historical note. So, recorded history of mathematics. Basically, we know whatever mathematics we know, it is from 2000 BC, and mostly from the Babylonians. They collect the wealth of and material of mathematics which we use and which we know today, particularly elementary algebra. Yet, as a science and mathematics as a science, it simply cultivated in the Greek soil, particularly in the 5th and 4th century BC. And I would say the pinnacle, the ever increasing contact between Orient and Greeks beginning at the time of the Persian Empire, when the Persian Empire were emerging, and it reaches to its climax when Alexandro arrived to this particular region, and he basically brought into contact the Babylonian mathematician with the astronomy uh, and definitely the ideas, the science, the math, exploration. It swelled in this land, particularly during the Persian Empire. So Babylonian mathematics, which spans from 3000 BC to 2000 BC, I should mention even 3000 BC. There are some evidences there. So 3000 BC to 600 BCE, the Babylonian had with a base of 60. So they worked with 60 base numbers. They don't have the same number system what we are using today. Instead, they use 60 base number, and uh, what they have done, so they tried to build the multiplication, and there are clay tablet which recorded the tables, multiplication table, and it is mentioned there 8 square is equal to 1 comma 4. So in the base 60, so 1 mean 1 multiplied by 60 and 4 mean plus 4, 60 power 0. So this is given there, and they built all the table, and they give also the squares of the numbers up to 59. And this was a monumental work at that time when people were trying to understand algebra. And an old clay tablet also revealed that even Babylonian 1000 year before the Pythagoras, they were familiar with the Pythagorean theorem, which is usually coined after Pythagoras. And they used to multiply in this particular way. So this is the Babylonian way of multiplying. Okay, the influence of Babylonian is quite visible even today. Till date, you can see that we are still using the 60 grids, 60 digit hexadecimal number system in time calculation. In every hour have 60 minutes, and every minute has 60 seconds. And similarly, angle calculation. So 1 degree, 60 minutes, and then further 60 seconds. So By the way, what they failed, the Babylonian, they could not develop the division process at that time. So division was not known to them. And let's talk about how mathematics evolved through rituals, religious rituals. So in the Hinduism, so whenever they have to worship something, so they need a fire, and a fire need to be okay for different uh, religious rituals. They have different fire altars. So in order to build the fire altars, they use a special kind of geometric construction where they use ropes and nails, and whatever the ways of the construction they come up, they call it Sulbha Sutra. So they record all those kind of construction in these books, which was basically written in 800 BC and 600 BC by these person Budhyana and Apastamba. Sulbha mean rope and Sutra mean ways. So what they have done a remarkable work, because they don't know the compass, they don't know the ruler at that time. So whatever they do it with ropes. And I'm just taking a clip here, so where they don't know about pi, so they use this rope and nail construction to prove mathematical proofs. And okay, one very simple problem which is demonstrated in the picture is that construct a circle equal to the area of a given square. And the reverse problem I will discuss later on. But this is one of the problem what they have proven in Silva Sutras. So just draw. So we are given with the square ABCD, and just mark X and Y. X and Y. You can see that just open. Okay, take the rope of that particular length and draw the circle, so that and then just draw this particular perpendicular bisector and mark this particular point. And by the way, they have given the complete ways how to build, how to construct the length one third, two third by using Sulba Sutras, by using Sulba, mean Rassi, rope. And and this is a proof. This is a quite remarkable work which was developed through rituals. Moreover, this is a human mind that they usually want to understand the big questions. So the big one of the big question of all time, what is the life of this earth? What is the life of this universe? And at that time, the time was during those eras, there was no years, no calendars were there. So they tried to build a particular mathematical method to understand the life of the universe. And this is one of the story which evolve, which is again given in Vedas, and they call it Tower of Brahma at that time. And nowadays people call it Tower of Hanoi. And according to the legends, they prescribed a particular way that if the 65 fragile gold disc plates move from one tower to the other tower with following a particular rule. And this particular rule is well known to any undergrad student nowadays, because Tower of Hanoi is a mathematical problem, mathematical way which is taught at the university level. By following the way, if the 60 when the last disk is moved, so it was written in their sculptures that there will be huge you can say earthquake happen, and ultimately the earth will destroy. And by the way, now we have a kind of calculation. If we say that we know the optimal way of moving the 64 disk without making a mistake, and if each move take us 1 second, so according to their Vedas, it should take 584.5 billion years to destroy the Earth. And by the way, uh, nova, supernova is expected to be 4.543 billion years, which is, you can say that the calculation what was written in the Vedas was overestimated. But anyways, the good thing is that the people were trying to address the question when they don't have the calendar, when they don't have the timepiece. They try to understand the length or the lifespan of the earth by using a mathematical way. Okay, if we move further, the Greek mathematicians, Greek era is the golden era, I would say, where geometry, mathematics, geometry, algebra, formal proofs were developed, and Greek mathematicians also contributed important ideas to number theory, mathematical analysis, and applied mathematics. And that was, you can say, the era where people started thinking mathematically. And I would like to name few of those Greek mathematicians. I think the biggest work during the Greek era was done by Euclid, and he has written a book which is named as Euclid Elements, and the book was written in around 300 BC. And that book has 12 volumes. In that particular book, he collected all the known mathematics at that time. And by the way, according to Wikipedia, according to all the information sources, the Elements is the most published book after the Bible. And even some counts even say it is more than Bible. The most published book is Elements by Euclid. It has 12 volumes. By the way, during that time of Greek, there was a mathematician who was quite a genius. His name was Archimedes. He did not only develop mathematics, but he worked on various things. So I think many of you are already know about his Eureka problem. He came across, and probably he's most famous due to this Eureka problem, when he gave the law of Archimedes and solve a mystery that why few things sink in water and why the other don't. And then he has built this iron kala, Archimedean kala. Is it is known when a ship goes okay, because he was a good mathematician, he was a mathematician, so he used to help apply his skill to save his country from the invaders. So Archimedean kala was a kind of a kala he built whenever a ship came closer to the wall of his city, so it simply topple it over. Then burning glasses was one of his discovery, which is said that which used to burn the mass of the invaders in the sea and drown them in the middle of the sea. Then one quite a remarkable discovery is Archimedes' tube, which used to delve the water in up to 200 feet. And by the way, in this whole slide, the most important picture is this one. So this is the process where you can see the circle in the red, and then you can see polygons inside and outside. So this was the biggest problem and biggest quest at that time to calculate or approximate the value of pi. And Archimedes way helped mathematician to approximate pi at that time. And this particular method was known as method of exhaustion, and that particular method of exhaustion lead to the discovery of you can say the discovery of calculus, what we are using today. And why Archimedes is so important. And let me just tell you, in mathematics the biggest prize is the field medal, usually near to many mathematicians. And the field medal has one mathematician picture embossed in it, the medal. So that picture is of Archimedes. And on the other side is his this famous result, the relationship between the volume of the sphere, volume of the cylinder, and the volume of the cone. And this is on the field medal, and Archimedes' picture is on the field medal. So if I talk about mathematician, if I don't talk about Archimedes, this is completely unfair. So Greek's Pandora box was quite at large. There were many important persons. One of the most important person was Zeno, and Zeno gave a statement which gave a real challenge for the understanding of time and space to many people at that time who were trying to understand the continuity. And this is known as Zeno's paradox. Let me just brief you. This is a very simple paradox. For instance, he said, assume an Achilles who can run really very fast, and assume a turtle. So in the at the beginning, the Achilles is at point A, and the turtle is at point T. Now let's assume that Achilles takes some time to reach from A to T. Okay. So Archelaus are step two. Archelaus arrive here, but during the same time, the turtle will occupy a new position. Okay. Then Archelaus run to the new position of the turtle, step three. And but the time it takes, during that particular time, the turtle will take up the new position, and the process will keep on continuing. And in this way, if you are kept on moving, the Archelaus will never caught the turtles, because every time Archelaus is targeting the position of the turtle, and the time it takes, the turtle will take the new. And that was the first paradox where people got to deal with the real challenge here, and that brought into the discussion the concept of infinity. And during people try to find an answer to this, but to solve this paradox, so by using mathematics and philosophy, and during that time, Aristotle, the person like Aristotle, he tried to give the concept of potential infinity at that time. And potential infinity concept was completely philosophical. So, whatever the number you think of, there is a number which is greater to that one. And that kept on using for many years up till the arrival of George Cantor. By the way, Pythagoras was very, very famous scholar, philosopher. He developed mathematics through music as well. So, music of the sphere, one can search and read how Pythagoras was doing the music of the sphere. And moreover, during the Greek time, this is the biggest invention at that time. The geometry got progress with the invention of the compass and the ruler. And why I say that this is the most important geometrical tool which was built at that time, because they came up with the problem. Mathematics always developed through problem. So they develop a problem which was reverse to what Hindus has discovered before. So they in Sulba Sutra they have given the answer. If you are given with a square, so you can always construct a circle which is equal of the area of the square. But what about the reverse of it? If you are given a square, can you construct if you're given with a circle, can you construct a square equal to the area of that particular circle? So that was the biggest problem at that time. So how to construct a square with the side square root pi by using compass and so the central part is this one. So I'm sorry. Okay. The main thing is that they have to, okay, let me just move the slide a bit so that, yeah. So the main thing is this compass and ruler. So can we construct a square with the help of compass and ruler having the same area as that of a circle? That was one problem. Then the second problem is, okay, can we construct a cube which is having the double of the volume of the given cube? Okay, by the way, even the reverse is quite difficult. If you are given with a cube, can you cut it, slice it to get the two cubes? This is not an easy problem. And I think this is the third problem you can teach it to any school kid. Can we trisect a given angle by using compass and ruler? So these three problems, you can say, so these was a Greek time capsule. So that is, okay, just like time capsule. So time capsule is a kind of a information, but they pass it on to upcoming generation. So Greek pass it on their time capsule by using these three problems. Do you know how many years it took mathematicians to find an answer to these questions? And how these problems evolved various theories in math? So one has to see the Renaissance. During the Renaissance, uh, Leonardo da Vinci, he was trying to understand the philosophy. So the famous picture of Vitruvian man who was standing like that and that. So that symbol resembles this particular problem, because Leonardo da Vinci was trying to solve this particular answer. And many mathematics and philosophical development evolved around these three problems. By the way, this problem and these problems are interlaced with each other. And it took mathematicians 2000 years to reach to find to the answer of these three constructions. By the way, these problems are known as problem of antiquity. If one would like to search on Wikipedia, they can find. And uh, uh, Greeks pass it on, and later on Gauss gave an answer. Watzel gave an answer to one of those problems, and then Lindemann. And at the end, in the 20th century, you can say David Hilbert arrived, who gave an algebraic answer. And by the way, the answers what Hilbert gave was from the recent development of mathematics, and which was not known at that time. But the problem was firstly thought by the Greeks. And let me just tell you the mathematics during the Roman era. You know about Julius Caesar, the famous invader. And Caesar has developed the first cipher at that time. So he developed the cipher wheel. So the use of mathematics in the army and the military. So that leads to new invention of mathematics, what is nowadays known as cryptography, or you can say encoding and decoding. By the way, for the sake of information, Caesar was very, very famous and very well known. The month of July is named after him because he was born in the month of July. So Julius Caesar, with the reference of Julius Caesar, it is named as July. And I during the Middle Ages, so you know this is the golden era of where algebra was introduced by Al-Khwarizmi, and many important discoveries arrived due to Arabs and in mathematics, and particularly many important questions were answered in that particular time. So, first time polynomials were taken into account in for the abstract study. People were trying to find the answers of cubic equations, and Umar Khayyam has given a method. Again, during that time of Umar Khayyam, usually the polynomials are considered only with positive coefficient, not with the negative coefficient. And people were trying to find the roots by using geometry. And this is Khayyam's method of finding the roots of a cubic equation. And by the way, during that particular time, people try to understand uh, epicircles. So this is the work of Al-Tusi, which is being later on used in engineering sciences. And then these kind of description taken so from uh, looking at, you can say, illustrative geometry to abstract geometry, abstract algebra come into play. And let me just tell you that Arab was not only trying to understand the work which is coming from the Greeks, they were trying to give answer to the question which were unsolved by many at that time. And one of that particular problem is the amicable number. So amicable number, this is very less known to mathematical community even today. Amicable numbers are the numbers if you factor 220 and you add the factors of 220, you will get 284. And if you factor 284 and you sum the factors of 284, you get 220. So Pythagoras at that time, he find out, I think he find out, he was able to find only one amicable number. And Pythagoras strongly believed that there is only this number which is amicable at that time. And amicable numbers are not no, are were known to Pythagoreans and who credited and definitely, you know, Pythagoreans were strong believer of mysticism, and they see some mysticism in these numbers 20 and 284. And by the way, there was a Iraqi mathematician whose name was Tehbat ibn Qura. You know what he did? He gave an algorithm to construct as many amicable number as you. This was a quite an astonishing result, and it has enormous application now. Amicable numbers, a general formula was given, and you can find on Wikipedia or something. So they were good in attacking problems too, and these kind of problems. I strongly because Pythagorean and later on Greeks, they were trying to understand amicable number, but no one. And Tebat Ibn Qura gave a formulation. Okay, geometry take a new turn when one European mathematician whose name is Lebre Abaci, or you know as so this particular person, Fibonacci, he took the knowledge from Arab, came to Europe, and brought all the wealth of the knowledge. And during the Renaissance period, people were trying to understand mathematics and art at the same time. And the first time projective geometry through the perspective, it emerges at that particular time. Leonardo da Vinci, he was a polymath. You can think of any person during the Renaissance time, any important, but they are all polymath, and they were trying to understand the structure of platonic solids. And okay, one very interesting chapter which is regarding to the root finding, was there in Italy. Italy has a culture that was quite interesting for the cultivation of science and physics. Not only math, even physics and art, everything was evolving in that particular time of the Renaissance. So there was a culture in their societies that any mathematician or any professor don't have a permanent position, so they always have a fear of a challenger who came in front of their office and publicly challenge them that solve these problems. And solving those particular problems, the challenge was only finding the roots of the polynomial. And at that time, the biggest mystery was the cubic polynomial. So how to solve cubic polynomial? So there wasn't any formula. People were trying to develop the formula, and they were not able to. There is a big question, and that's why people try to build difficult polynomials and challenging the challengers to solve the answer. If a professor was unable to answer the question given by the challenger, so the challenger get the position of the professor. So this is the kind of street fights were happening in Italy. And during that time, there was one person, Tatalia, who came up with the formulation, but he kept it hidden so that he get his position secure. And that secret formula story you can find on Wikipedia or anywhere. So this was a very interesting chapter where people invented something, but they hide it from the eyes of the others to keep their position secure. Okay, there's always an important debate when it comes to mathematics. You have seen that people are studying mathematics from practical uses, from philosophical point of view. So there is always a debate: what is more important, applied mathematics, or you can say the foundational or pure mathematics. So there was a, I think, one of the leading Russian philosopher is Tolstoy. He explains and writes somewhere that sciences for the sake of science is an absurd conception. And definitely one cannot know all things. He said definitely all the scientists, all the mathematicians, when they study or they research something, so they do a careful selection of those particular topics. And isn't it possible that why don't they pick only those topics which are useful, which have some utility, which has some application? And the curiosity driven questions are of no use, according to Tolstoy. So this was his point of view. And this was responded by, I think, the leading mathematician of that time, Henry Poincaré. And he has written a note with the title Apology for a Few Fools. Scientists believe that there is a hierarchy of facts and that a judicious selection can be made. And they are right, for otherwise there would be no science, and science does not exist. One has only to open the eyes to see the triumph of industry, which have enriched so many practical men, would never have seen the light if only these practical men had existed, and if they had been preceded by disinterested fools who died poor, who never thought of the useful, and yet had a guided, and that was not their own caprice. If they had worked solely in view of the immediate application, so this is the very important line he said. If they have worked solely in view of immediate application, they would have left nothing behind them, and in the face of a new requirement, all would have been to be done again. So definitely I think the best part of this particular debate and discussion was encapsulated by Freeman Dyson in his famous article Birds and Frogs. So according to Freeman Dyson, there are some researchers who are birds who are linking the area with the application, going from one area to the other area. And there are some mathematicians who are good in working in their own area. So for the health of the whole system, it is better to have birds and have frogs. And there is a mathematician who saved 14 million lives and during the World War II. His name is Alan Turing. And let me just tell you, in computer sciences, the biggest prize is named after Alan Turing. The Turing Award is the biggest in computer science. This is a dream for any computer science person to win the Turing Award. And by the way, we are living in the era of AI and ML, and The idea of the AI, artificial intelligence, was firstly coined by Alan Turing, and that was his unpublished work. And you can see the impact of his ideas and theories in today's life. And you can say we are viewing the magic, the wonders of AI every day. So, mathematical Pandora box would not be complete if I don't talk about calculus. So, I there is a famous article which was written by Eugene Wigner, who is a Nobel laureate, uh, the effectiveness of mathematics, and he said that the enormous usefulness of mathematics in the natural sciences is something bordering on the mysterious, and there is no rational explanation for it. Because in physics, all in a sudden, iota started appearing when people tried to understand the Schrodinger behavior of the wave. And iota, initially, this appeared only in the roots of the polynomial, and physicists strongly believe that they have nothing to do with iota and complex numbers. So all in a sudden, iota started making a complete sense when Schrodinger defined his operation, gave his equation, wave equation. And before that, I would say that these two gentlemen, Pere di Fermat, René Descartes, you have seen in the first slide too. So these two men are credited to laid the foundation of analytic geometry. And by the way, they both of them worked quite independently. Seldom they used to write letter to each other. They live in around the same time. And later on, working independently, Sir Isaac Newton and Gottfried Leibniz, again, both of them worked independently. And there is always a fight to give the credit, whether it was Newton or Leibniz who invented calculus. So definitely, calculus is, you can say, the pinnacle of the mathematics developed over the years, which started with the work of Archimedes. And by the way, this duel of achievements unlocked the gate of wisdom and sharing in a new era of mathematical understanding and paving ways to countless discoveries and applications in various scientific disciplines. And by the way, according to Stephen Hawking, in his book God Created the Integers, Newton could never have formulated his laws without the analytic geometry of René Descartes. And you can see that. So these two men were trying to understand the behavior of the curves and analytic geometry. People, both of them were trying to understand the behavior of tangent along a particular curve. And René Descartes, particularly, we usually call it Cartesian plane, which is named after René Descartes. He has given so much to the analytic geometry, and all those techniques were warmly adopted by Sir Isaac Newton and Leibniz to develop the ideas of the calculus and particularly the fundamental theorem of calculus, which connects the two different concepts, differentiation and integration. And now it has emerged that whatever physical phenomena you look around, there is some derivative engaged in it. And if I talk about mathematical Pandora box, so it would not be completed without the discussion of Fourier. Joseph Fourier has given Fourier transform, and these Fourier transform are used in wide application, broad application, circuit designing, spectroscopy, crystallography, signal processing, all communication, our mobile phone, in the computer we are talking through. So many European mathematics were prominent mathematicians, including the name of Euler, D'Alembert, Bernoulli, Lagrange, Dirichlet, Poisson. They all developed the theory of analytically, this particular theory. By the way, let me just uh, embrace my audience with the fact that it was not Joseph Fourier who has given the idea of Fourier transform. The idea was given, started with Euler, D'Alembert, Bernoulli, Lagrange, that the idea was quite simple, that any function can be any function which satisfies certain mathematical condition can be described as a summation of sine and cosine in the series of sine and cosine. But the real issue was that at that time was the convergence of that particular series. And if the function is periodic, so non-periodic, how to deal with non-periodic behavior. So that particular, and particularly the convergence. So Fourier credited to resolve this particular issue. So Fourier work basically lies purely in pure mathematics. He showed the convergence part. And by the way, the theory already existed, and those persons, those names were responsible in building this particular theory. And by the way, today we know it is as Fourier transform. It is coined after Fourier, and Joseph Fourier's contribution to modern day engineering sciences are so critically important and so pervasive that he is regarded as the father of modern day engineering. So it is. So I forgot to tell you, Alan Turing is known as the father of modern day computing. So Joseph Fourier is named as father of modern engineering. And wisdom from great men. This is the important point. If great men write, why not to read what great men write? And it is a sad commentary to our education system to note that in math courses, every student is required to read many books by educators, but they are never required to read even a paragraph by a great science, such as the greatest man of science like Aristotle, Galileo, Kepler, Newton, Fourier, Lavoisier in chemistry, and Maxwell in physics, and as well as mathematics, you can say. And there is a great word observation which was said by German philosopher von Humboldt. He once observed that any popular reaction on any important discovery it goes through three phases. So the first phase is firstly men deny its existence. This is not possible. And the second phase then deny its importance. If it exists, people say that okay, it exists, but it is of no use. And the third thing and the last thing is that, and at the end, they give credit to someone else. So this is something which is quite common in when people talk about mathematics. I try to cover all the important paradigm where you can see computer science, you can see physics, you can see philosophical, even the thinking thought process. So mathematics is engaged in almost all the fronts. But whenever people talk about the development of mathematics, people are too obtuse in opting that, okay, only probably the mathematics, which is quite applicable. So all we need only engineers. Probably mathematicians are not as important as an engineer. So there is always a debate of radical and rational thinking to deal with mathematics. So one should remember this von Humboldt quotation, which is quite important. At the end, uh, I take this thing as my duty in each of my talk. I try to introduce some important books from where I try to get the details, and moreover, this is good for those who would like to delve more in knowing the mathematical history. So particularly mathematical history and recent time mathematics and mathematics for various purposes. So the first book is freely available. This is called Living Proof, and it is available. It contains the stories of the resilience of many famous mathematicians whose pictures are shown, and this book is available on Mathematical Association of America webpage, and I think it is still developing. And it is really very good to read how people transformed into mathematics when they were struggling even at their school age. Even some people were struggling at the university time to get measures in mathematics, and all in a sudden they turned to a mathematical geek and become a big iconic figure. Then there is a second book which is quite important, and I will talk more about Francis Su in my last slide. So Francis Su is a Chinese American. He has a strong belief that uh, for human flourishing, mathematics play a very important role. What is the meaning of a good life? And this is a kind of a case he had made in this particular book. And this is quite an interesting book and very good book. And by the way, he also remained the president of the Mathematical Association of America for so long, and he has given a lecture. I think this is the only lecture in the history of Mathematical Association of America which got standing ovation, and this was on this particular book, and the lecture is still available on YouTube. You can watch that lecture, and you can view his views about human flourishing, how mathematics can play a role for human flourishing, and he tried to explain it through the story of a person who got convicted and who is in a jail, who is waiting for he got lifetime prison, and what to do in the jail in the free time. So he started learning algebra, calculus, and how his life transformed. And by the way, he recently posted that they have appealed for reducing his punishment because he has gained a lot of understanding in mathematics. And by the way, this is true story, completely true story. This is mentioned in this book. And then I think this book by Stephen Hawking, God Created the Integers. This is a wonderful, wonderful book where Stephen Hawking tried to encapsulate the stories of leading mathematicians from Greek time, almost all those which I mentioned, and there are many others who worked in development of mathematics during the different eras. And I think there is no match to this book as well. And then the book by Steven Rogards. Uh, to read the book of Steven Rogards, you don't need high level math. So you can come from a school background and you would like to know how the calculus was evolved during the different era. So this is a book which will enlighten you, and you can read more about the development of calculus during the different eras in this particular book of Steven Rogards. And this is also the New York Times bestseller of all time. And at the end, I would like to recommend a Quanta article. So you can watch a YouTube video, you can read books, and you can read the Quanta article, which is again by Francis Su on this book. So ancient Greeks, according to Francis Su, they argued that the best life was filled with beauty, truth, justice, play, and love. So these are the five components what Greeks come to the conclusion when they define a good life, or in other words, the best life. A best life should have these five components. And according to Francisco, this is the case he had made in his book, and quite remarkably, he presented in his talk. And moreover, in this particular article, a Quanta article, which basically this article is about his talk, which I mentioned, which is available on YouTube, and one can read this article. And this is the slogan: to live your best life, do mathematics. That is the end of my talk. Thank you very much. So I'm ready to take questions if there are any.
Yeah. Thank you so much, Dr. Imran Anwar. Really wonderful talk. Now I welcome any question from our audience. We will address them during the question, of course, and answer session by considering the Dr. Imran Anwar Sahib. Here are three questions from the audience. I would like to request to consider them. At first place, the question from Shazia. She's asking, what would you remark on the idea of harmonious life if both spouses are mathematicians, implying a symmetry in their shared pursuits?
I think she might be talking about my second slide.
Yes,
Yeah,
yeah,
I would say that I think Feynman wife. I believe she was interested in physics, but I believe at the time of George Booley, his wife was. By the way, George Booley's wife was huge admirer of George Booley, but I don't. She was, but it can be understood during the year 1864. The medical sciences people were trying to. So she was a homeopathic. You can say a home therapy and simple treatment method. She strongly believed, and by the way, she loved his husband a lot. Even this is a note I have taken from somewhere, but definitely she mourned a lot on his death. But by the way, I have no answer if both of their wives were math geeks. So probably they would
yeah.
George Bully would live more.
It's really
Yeah.
difficult to find the symmetry. Anyhow, Shazia, if you are here, would you like to ask something more from Sir Imran Anwar, please? You can unmute your mic if you are available. Otherwise, uh, if I would like to proceed to the second question from Fatmatul Zara. She said, we acknowledge all the discoveries by mathematicians. But what is the purpose of all kind of research that we are doing in mathematical fields if we are um, unable to find any use of all these findings even after 50 or 100 years now?
That is a very, very important question. So, in during all my talk, whatever the questions mathematicians were dealing, so mathematical research and the barometer of mathematical research should be based on the central problem of mathematics. That is the only thing one should tie up their motivation to the central problems of mathematics, which attracted the interest of leading mathematicians. And if we talk about what mathematical research are important, so people worked in various disciplines, and definitely mathematics has a lot of branches, and everyone has different interests. So, but the main thing is that when you are trying to find the importance of a particular problem, so that could be well understood. Either it is a central problem, number one. Number two, either this particular subject is being treated by, is being uh, treated high regards, getting high regards in the mathematical community or not. So, if we talk about these mathematicians, whether there is a field medalist in that particular area, whether there are talks in the Congress, in the International Mathematics Congress. So Congress talks are the good barometer to pick and select the area where to work and what mathematical community values.
Yes, we
That is
noted
amount.
in the recent field medal awards, mostly people have been selected from the pure mathematics areas. So this is another, you can say, the comment on that. However,
Yeah, but there are few partial differential equations as
yes,
well, and people are working trying to Navier-Stokes problem is one of the central problem.
exactly.
And
Fatmatul Zora, if you want to ask some more question from Professor Imran Anwar Saib, please speak out. Okay, they may ask at the later stage. Sir, there is one question from Muhammad Shoaib. He was very interested in your nominated books, and he was asking where to get these books in PDF for free. Just the
okay,
question.
the
In the some link or some software you can guide us, please. Thank you.
Okay, Living the
Yeah.
Proof is freely available to anyone.
Okay.
You just Google
Thank
it,
you.
and you will get on the web page of Mathematical Association of America. It is freely available. So regarding the other books, I would recommend. Okay, there is a big issue with mostly Pakistani universities. The library budget is not being capitalized. So it is good
Yes.
to go to your librarian and ask them to get these books for you. And the last thing which I don't want to say on air, so you can find ways. So there are websites from where you can download books, and one of them is Library Geniuses.
Okay, very well noted, sir. Very well noted. Sir, there is one more question from Izhar. That can you please elaborate on the resilience that the set theorists, for example, how they define the axiom of choice?
Yeah, Ishar, this is something I could not say much, but on the foundational work of the axiom of choice, there is a lot of debate because this is one of the hot question, and even that challenges the existence, particularly the concept of real numbers, and there are some assumptions on the basis of which the foundation of mathematics people were trying to fix, and that is still there is still a crack there, and there is no fixation to that. And great mathematician like David Hilbert, he carried out this particular project of fixing the foundation of mathematics. But later on, Kurt Gödel arrived and he said that it is not possible. And he has given the Gödel paradoxes, and which was unfixable. And later on, David Hilbert turned to other problems of mathematics and he developed Hilbert spaces, which solves the problem for quantum mechanics and in physics. And there is a famous article by Arne Mahar, Gardening in the Neighbor's Garden. That is on David Hilbert. He used his mathematical skills to solve the problem in physics. But I'm sorry, Izhar, I can't say much on that particular front. I'm not an expert.
Okay, that's pretty fine, sir. Uh, Let me confirm. Few fellows would like to talk, speak out their mind. If they may allow to unmute their uh, mic, then I think they may will talk. Muhammad Izhar. Um,
Hello.
Yeah, Izhar.
yes, yeah, please speak out, please. Thank
How?
you.
Thank you
Sorry,
for giving me a chance to talk. First of all, thanks, Imran Anwar, for such a nice talk. Actually, I just wanted to point out, since you were talking about the resilience the mathematicians have shown throughout the history. So I personally felt that set theorists have been on target much more, since first of all they couldn't fix
I
their definition of a set,
Yeah, I can understand. Yeah, exactly. Exactly.
and then now they are unable to fix um, their axiom of choice. So I actually try to contribute to the in a way to point out the resilience the set theorists have shown in during the
Yeah,
last.
Izhar, I understand your point, and thank you very much for bringing this particular point. I missed this point, very important point. I was having the name of George Cantor at that particular point. George Cantor was the first one who tamed infinity, particularly, and gave an idea that infinities can be different from one another. And ultimately, he arrived at an hypothesis which was quite lethal for him. Ultimately, he died in asylum, and he caught up in a loop. One day, he writes that I found the answer for continuum hypothesis, but next day he said that it was wrong. He gave the counterexample himself, and he died in a quite a miserable situation, and the whole mathematical community didn't value his ideas at that time. He was opposed by Henry Poincaré, he was opposed by Kronecker, and he got very less support from the mathematical community, the set theorists, and he's known as the father of set theory nowadays. And the second person is Kurt Gödel. Kurt Gödel was having quite a good time until unless he started dealing with the same problem of continuum hypothesis. And when he started this particular problem, he caught up in the loop, and he got a very you can say that mathematicians are very bad toward their wives. Kurt Gödel has a very strange habit. He used to ask his wife to taste the food first, because he was having an hysteria that he will be poisoned, and he used to, whatever the food was offered to him, he firstly asked his wife to taste to be sure that it is not poisoned, and then he takes the food. And when his wife got tired and he was dealing with the continuum hypothesis, so it was said that he stopped eating due to that particular hysteria, and ultimately he's a mathematician who died of starvation. So these are the two. I think Ishar made a very important point. The number theorists were always under fire. So though Kurt Gödel never got any such resilience from the mathematical community, but George Cantor certainly has. Certainly has. Thank you, Ishar.
Yeah. Thank you so much, Muhammad Izar, for asking, and all the others for bringing the wonderful question. As we come to the close of today's webinar, on behalf of ECOSF and UISMS, I extend my heartfelt gratitude to Dr. Imran Anwar for his thought provoking and insightful lecture. I also want to thank all the participants for their active engagement and interest. We anticipate hosting more sessions, bringing learned scholars from the ECO member countries to promote and popularize mathematics and science among our young colleagues and students in the future. Thank you so much. Thank you, sir,
Thank
once
you.
again.
Thank
Yeah.
you, the organizer. Thank you, everyone, for your time. Thank you.
Yeah. Thank you so much. Please.